Good evening and welcome to the Hereford and Worcester local network presentation this evening on the LoRaWAN. I'm Rick Barfoot, the secretary of the local network, and we'd like to welcome the members of IOT, the LoRa Alliance, and indeed the general public. Before we go into the details of this evening's event, I'll just advertise our next one, which is on the 14th of June, and this will be dealing with battery-powered trains and how you charge them rapidly in this new electric era as we go into the future. Turning to tonight's event, the mechanics of the event is that Derek will present for half an hour or 40 minutes or so. We'll then have questions and answers at the end using the Q&A chat, and Peter Carney will manage the Q&A chat. If you'd like to provide any other feedback, use the normal chat feature. Particularly if you'd like a CPD certificate, you can either put your name and email into the normal chat or provide that information in the feedback after the event, and I'll then email you a CPD certificate. Also, I'll paste a link into the normal chat, which is the IET survey they're currently conducting this year to really measure and assess the communities that support the IoT, particularly in the local areas. So let me turn to our tonight's speaker, Mr. Derek Hunt. Our last presentation on IoT in February, Peter Carney presented the Internet of Things and its use in the breaking of the land speed record. In that particular event, we had a lot of questions about communications and security of communications, and Derek kindly offered to present to the IET Hereford and Worcester, a later event, that's tonight, to explain that. So Derek has 30 years experience in the telecommunications industry. He is the Director of Certification of the LoRa Alliance and also the Chair of the Certification Committee. So a lot of expertise in this particular subject area. So Derek, I'd like to hand over to you, and we look forward to the presentation.
Thank you very much, Rick. So first of all, I'd like to start and welcome you all to this IET presentation. As Rick has said, I am the certification chair of the LoRa Alliance, and I actually started my involvement in the LoRa and LoRa Alliance back in 2014. I worked for Semtech at the time that acquired a company that had the technology and was really working on the very early versions of what later became the LoRaWAN protocol. And in fact, one of my claim to fame was out of the group that were doing it, there was a lot of Swiss, French, German people in there, and I was the only native English speaker in there. So I rewrote a lot of the very first version of the LoRaWAN to try and help put it back into some sort of resemblance of grammatical English. So what I wanted to do really on this one was just try and go through a bit more detail about the engineering side of LoRaWAN and the protocol, and really give you a little bit of feedback about how it started and some of the thoughts and ideas that were behind it. So what I want to go through really is just a couple of sort of general issues that everything in the IoT world has of it's got to try and get the data back to the cloud. How does it do it and what are the challenges? I'll do a very brief overview of LoRaWAN, a little bit about the Alliance, and then I'll dive into the technical view of LoRaWAN. So as I'm going through, if you want to just keep your questions coming in on the Q&A box, and then at the end of it, we'll try and go through and answer as many of them as we can. So to get started, so the real issue is we have a lot of devices out there, and the one thing that really they all need to do is get connected back to the internet. And that can present a lot of problems for some devices. Others, it can be a fairly straightforward one. If you have something in a building that has a reliable internet connection, obviously that's a straightforward way of doing it. But the vast majority of cases where we really want to connect things are in areas that are more remote, where the chances are there is no Wi-Fi. In essence as well, there's very unlikely to actually be any cellular connection either. And the other thing is, the majority of these devices are going to be very small, very inexpensive, and more importantly, they're going to be battery powered. So what you have to make sure is that whatever technology you come up with, it is very efficient from a battery usage point of view and from a size point of view. So those are really all of the challenges that you face. With Wi-Fi and cellular, obviously there's a large power consumption, and any device that you want to last, especially if you want it to last 5-10 years out in the field, unless you're going to stick a huge battery with it or do some sort of other farming of power from solar or whatever, then it's got to be power efficient. And also the other side of it is it's very expensive to set up the traditional networks. There's bidding going on, obviously, for all of the different radio spectrum. And so really they end up making it far more expensive to try and set up your device or your network. And really what you want is the flexibility. So one of the things that I'll go through really with LoRaWAN and how it works is, because it works in the unlicensed band of the ISM, it is actually free to set up and free to run. So what I'll do is, that's some of the problems and issues that we've seen actually getting connected. So what I'll do now is just quickly run through the sort of overview of what LoRaWAN is and then go on to the LoRa Alliance. So really it's been aimed for massive scaling and deployment. It's set up by the LoRa Alliance, which I'll talk a little bit about, as a non-profit organization, and it's set up as a proprietary standard. And the real goal, as we said, is to get millions and millions of devices connected together. It has become, probably over the last couple of years, really the de facto standard for LPWAN. And that's really why I thought it was useful to try and cover and describe what it does. And really its key strength is it covers so many different market verticals. One of the things that's always astounded me every time I've been to a conference or every time I've talked to end users, the number of different cases and the number of different ways people have come up to do this, from monitoring cows to monitoring traffic or tracking things, checking for water leaks. Really, the number of different verticals that it can be used for is endless. So what does it offer? So really, this top level view just says it can be deployed in lots of different options. We have public networks, which are done by traditionally mobile operators. We have private networks, and we have networks that are effectively hybrid. And with all of those, they can be a combination of them both. So quite often we actually see people start with a private network. They may want to just monitor something inside their factory or building. And then at some point they say, okay, I now want this to actually go across and be monitored when it goes across the country or to another office or building. And so they typically start with a private network where they put up their own gateway and connect their own network server to it, and then look at, okay, now there's a public network available, how can I do that? And the whole thing is it's scalable and easily to do. And the CapEx for setting this up is very easy. Basically one gateway and a network server connection via the internet, and you're pretty much up and running and going. It can, and I'll go through the detail, handle multiple devices at any time. It's very quick and cost optimized. So I won't go through all of this thing, but in essence, it also can provide geolocation, which is network driven. So you don't have to have any specific equipment actually in your device. So it doesn't need any GPS or anything like that if you don't want it to, because that again is a very expensive power consumer. We also offer double layer security, and I'll talk a bit about that, about between the device and the network and the device and the end application. And obviously the key is to try and give you a maximum life battery out of this. And there's lots of different cases that you can use to try and get the most out of your device. It's very scalable, and I'll have a little slide that will show you how easy and quickly it is to scale for that, as well as talk about some of the roaming and things that we're doing with other ones. But more importantly, the reason that it's really been successful is effectively its ability to penetrate deep indoors. So when we start looking at the physical side of the device and LoRaWAN in particular, you can see that it has the link margin to be able to do not just large coverage, but also get deep inside where necessary. So just a little bit about global networks then. So LoRaWAN has been adopted, and you can see by 150, well, over 150 operators now worldwide, and covers 173 countries. sorry, 163 countries. But what we've been able to do recently is offer roaming capabilities. So here, for instance, and if we even look at Europe, we've got roaming agreements in place. So you can start off with a device in one country and roam across using the network operator in the following country to actually pick up your device. So this really has helped get that global coverage. And you can see we're pretty much covering most parts of the world now in some form of LoRaWAN. So one of the questions we always get asked is, what's the difference between LoRaWAN, and NB-IoT and 5G? And I think this is the simplest one to really look at. Both of them will exist. Both of them do exist currently, but really they're aiming at slightly different markets. LoRaWAN and LPWAN in particular is really good for the sort of massive IoT, where it's very low power, very large numbers, and very low data rate. And that's really where its niche is. And that's probably where the majority of sensors are and are going to be for years and years to come. Obviously, if you look at NB-IoT, it's much more high power, much more larger power consumption, higher throughput, and is really used for other areas. So in particular, sort of smart grids, anything you need large volume of data, so video security and things like that. Those are the ones that are going to be working based on NB-IoT. But for everything else, and the majority of sensors that we're seeing, you want the low power and long range, and that's really what LPWAN and LoRaWAN offers. So just a little bit about the Alliance. It was formed in 2015. The goal was to develop the protocol as an open standard and de facto standard for LPWAN. We have more certified devices on the market than any other LPWAN technology, and I've been proud to drive and generate that certification program for the last sort of 5.5 years, or 6.5 years now that I've been with the LoRa Alliance. And really, we're a non-profit organization, and as you can see, we have members from across the world all using the technology to basically set up their own networks, their own devices, and effectively do what everyone really wants to do, which is monetize this, get connections back to the internet to allow you to actually track, control whatever you want to do, and effectively see a return on your investment. From a member's point of view, there's a whole list of, and I won't go into all of them, but it's basically split into sponsor members, contributors, and adopters, and institutional membership. But we have members going across the world again with this. And obviously each one of those brings something to the party. So the whole sort of ecosystem that we have is from chipset manufacturers to module manufacturers, devices, right the way through to gateways, servers, operators, cloud, and solutions. So really the whole thing, members of the LoRa Alliance cover the complete range of the ecosystem necessary for you to actually develop your system and get it out there. So that was just a very brief overview of the LoRa Alliance. Now what I want to do really is go to the bit which I was going to concentrate mostly on this webinar and talk about the technical side of LoRaWAN. So the first thing, and this is one of the slides I always find is probably the sort of interesting one to try and look at. We've said that LoRaWAN and the LoRa Alliance technology works well. Why does it work well? And it's really about this sensitivity and range. When you actually look at getting, and I won't go into the full details of it, but the sort of 148 dBm sensitivity from a device, you can see compared with Bluetooth or Zigbee or even FSK, the enormous extra range that you can get using the LoRa chipset. So with that, it allows us to really make the most of the technology. So from a LoRaWAN point of view, we can see the long range and low power, and more importantly, small form factor. So this is talking about the European ones, but obviously we work all over the world, and there are different power outputs and different requirements for different countries and different regulations around the world. And I'll mention a little bit about those as well at the end. But typically we can sort of see for a 14 dBm output power, we can get 2 kilometers in a dense urban area, 15 kilometers in a suburban, And if you can go for line of sight, you can get 80+ kilometers, and all of that with a 10-year battery life. It really is a simple network to set up with just basically a star network. One of the things that's in here is the link data rate adaptation, and I'll talk a lot about that as we go on, because that's one of the key advantages that we actually have with LoRaWAN. And obviously, gateways are quite able to capable for millions of transactions per day. It's a fully bidirectional system. It has all the built-in security in it and an easy network management, as well as allowing us the broadcast function. And when we talk about firmware over the airs and things, we make the most of that broadcasting functionality to do that. So you don't have to talk to just one device. You can effectively do a firmware update by broadcasting to multiple devices through a multicast arrangement. It's also very robust to interferers and very difficult to jam. If you look at a lot of the issues we've seen, and we've seen a lot of these devices now being used to either support or looking at protecting expensive and valuable cars. You see so many cars now have already built-in links back to the network, but because they worked on GPS and GPRS and others, they're very easy to jam in comparison. With a LoRa Alliance or LoRaWAN network, you would need a large piece of equipment and a very high power if you actually wanted to jam it. So we're seeing a lot of people using these as a secondary one, where even if someone comes in and the carjacker puts a jamming device in it, it's still then able to communicate through a LoRaWAN network. And the location ability for it to be able to pick and define roughly where a device is without needing to have a GPS on it is crucial. So just a bit about the technology, and I won't go into too much detail about this, but effectively it's called what's spread spectrum. So basically it takes the normal signal and then spreads it and effectively modulates it across the whole of the frequency range. And what you get left with is something which actually looks like this here. One of the key things you can see is it actually takes it, once it's spread like that, below the noise level. So one of the things that actually helps us is if you're looking at other interferers and things in there, even if the signal and the noise level drops, there's still likely and very likely that you'll still be able to pick out your signal when you go through the demodulation because of that. And that's what again helps it to be robust to jamming and interference. And one of the other things that's really useful about this is the spreading codes. This is how many channels you're actually multiplying it with. Effectively, each one of those, so whether it's SF7, SF8, SF9, which are the different ones you modulate it against, all the channels that you create are effectively orthogonal, which means they don't interfere with each other. So you can have a network that can run on the same frequency, but use lots of different spreading factors or data rates, and they can all communicate successfully without interfering with each other. So that's really what's behind the technology itself. And it's this ability now that we are using with that very high sensitivity figures to create the rest of the LoRaWAN implementation. So I'll go on to a little bit about the architecture, and this is always my favorite slide to talk about the architecture of it. I think on this one slide, you can summarize effectively the whole of the LoRaWAN architecture. So if we start with a typical end device, and it could be any type of device that you can imagine, from trash containers, gas meters, vendoring, smoke alarms, whatever. The key thing is you have an end device. And one of the things that I will say at this point is when we looked at the design of LoRaWAN, what we always tried to make sure was that if there was ever any complication in the network, the place that we would push it to would be the network server, with the goal that you always keep the end device as simple, as easy as possible. Mainly because that avoids any additional messages going down, but secondly, because again, you're trying to make sure that this is the minimum power consumption. So what happens is a device might suddenly say, oh, I've got an alarm, the smoke alarm, something's set off. So the device has been configured and set on the network, and it may have sat there for a day, a week, depending on how often you want just a keep alive message or a message from it. It could have even been a month since it last communicated. but effectively it's set up and it doesn't have to do any separate keep alives. It's not like something else where it regularly expects to do it. It's set up and ready to go. So at this point, the smoke alarm wakes up and says, I've got an alarm. I need to send a message. It doesn't know who it's sending it to, and it doesn't care who it's sending it to. It literally just wakes up and says, I've got an alarm. I need to send the message. And for this smoke alarm, you can see it's actually gone and been actually picked up by 2 gateways. And again, this could typically be in your own private network, or this could be in a public network where you've had a gateway from an operator. So what it then does is the gateway at this stage really is a fairly straightforward packet forwarder. It decodes the LoRaWAN side of it, which is on the radio link, and then actually just converts it into a TCP message and then backhauls it. And again, these gateways can either be through TCP, or we could use a 4G or a 5G internet backhaul to get back to the cloud and the network server. So we've got to the point where the smoke alarm's gone off, it's sent a message to the gateway's picked it up, and it could be, as you can see for the water meter, it's picked up by 3 gateways, it could be picked up by 5 gateways or 10 gateways. You really don't mind. In fact, the more gateways it gets picked up by, the better. But then those messages all get through and sent to the network server. What the network server then does is say, okay, I've seen this message coming in, and it may come in from several gateways, which is fine. What it will do is it'll just collect the information about the signal strength that these different gateways have been received on, and that information is forwarded through to the network server. But then the networker says, this is a smoke alarm, right, I need to do something with that. So what it will then do at that point is pick whichever application, and this is pre-programmed, so it knows which application server it wants to go to. It'll go to the application server and say there is an alarm. Now, at this stage, there could be some response back that you want to go back to the device. So at this point, the application server would say, okay, I have a message I want to send back down to it, which could be raise a local alarm, call something local, turn the lights on, whatever you want it to be. So what it does is it sends that message back down to the network server. Now, what the network server says is, I need to get a message to the smoke alarm. Now, when I saw the message coming upstream, I could see it was connected via these 2 gateways. So I'll have a look at the RSSI, the signal strength indication, and the signal to noise ratio that was provided with those, and I'll pick which is the best gateway to send the message back down to it. So in this case, it could have been this one that was the strongest, and it will send the message back down to that to transmit to this. And the way that it works in the standard class is the smoke alarm sends the message, and then either 1 second or 2 seconds later, it will open a reception window so that it can actually receive the downlink message. And effectively, it receives the message and then does whatever it needs to, or goes back to sleep again. And the whole mechanism of how LoRaWAN works is that simple, that a device wants to send a message, it wakes up, sends the message, listens 1 second or 2 seconds later for a return. Is there any response to me? If not, fair enough, I'll carry on, and I'll carry on either monitoring or do whatever I need to do. So what we've got built in on top of this then, and security is one of the big areas that we are worried about from this side, obviously, is we've built in, as part of the LoRaWAN architecture, AES 128 security, and there's 2 levels of security here. So first of all, there's a security and a separate key and session key that runs between the end device and the network server. But then this could be a critical application, it could be a banking application where you don't want the network server to be able to see your data, which is typically what happens with mobile networks now. So what we've then got is a second secure link, which is between the end device and the network server. And so this double layer of protection on here not only protects against radio and anyone trying to listen over the radio link, but also that even if the network server can see the end device and can talk to it and control it, it still cannot actually see the application data that goes through it. So in essence, that's basically how it does. And I won't go through the text because I've probably much described that at the end of it. So apologies, this one's a little bit complicated, but we talked in a little bit about spreading factors and data rates. And these are some of the typical sort of data rates that you can get from the device. So I've said that it will run at different spreading factors. And there's a couple of key things to do here. So the key thing to remember is the spreading factor determines the actual end device sensitivity, which will also determine the range. So you want the biggest range possible if you want to get the furthest signal. And as you can see, as you start going up in data rates, then the payload and the data bits per second goes up, but the sensitivity is coming down. So at this point, you're then actually reducing, you're getting a faster data rate, but you're reducing the range over which that is being transmitted. And effectively, a LoRaWAN gateway and a LoRaWAN device can use any of these spreading factors or data rates when it's doing its communication. And again, this is one of the key things that's sort of typical to how LoRaWAN works. And there's a couple of things of, we've seen some devices that don't use the LoRaWAN, but just configure the device as standard. And typically that means that they are hardwired to this one, which means they get the range, but they have no ability to step up in terms of data rate and things. So they're really losing a lot of the ability of the network. So the key things to remember from this is as the data rate goes up, the distance that it travels and the sensitivity goes down. And then the other bit is the time on air that's actually needed to do this. So you can see if you're running at a very slow speed, for time on air of 1.4 seconds, if you're trying to transmit a typical 10-byte payload, that means your transmitter has to transmit for nearly 1.5 seconds. And that is what's using a lot of the power. So the other thing to get the maximum power out of your device is to keep the transmission times down as small as possible. So you're always trying to get down to the point where you can go for the much faster data rates, which keeps the time on air, not just to send, but also while you're listening to receive, down to the bare minimum. So this is what I'd call is probably the most key feature in LoRaWAN, and it has what we call the adaptive data rate control. And basically what it's saying is every device is individually controlled by the network server to set the data rate. So if a device starts up, it might start up typically over here, a long way away from the gateway, or when it first starts up, that's what it assumes. What it then does is, after sending and receiving a few messages, I said as well that the network server can look at the RSSI and the signal to noise ratio to determine which was the best gateway to send it back to. But what it also does is it runs that through an algorithm that says, okay, you're now talking at the slowest data rate, but I can see from your signal to noise ratio, you are very, very loud to me. So what I can do is the next link message I get to you, I'm going to tell you to move from data rate 0 to data rate 3 or data rate 4. Or if it's really strong, I'll get you to move all the way to the highest data rates. And that ability to individually control each separate device is really what makes LoRaWAN so useful. So you can go from something that was a long way away from your device and driving and running quite slowly, right the way through to something as it gets closer to the gateway, and this could be a static device or even a mobile device. There's a little bit of a time lag for mobile, but what it allows you to be able to do is optimize really the data rate that the device works so that you get the best radio performance for it. And typical examples we see of this are you have a street parking and you could have a sensor over your street parking meter, which determines, yes, a car's now parked here. So clearly at that point, you've got a big lump of metal in the way, and the chances are you'd need to run at a slightly slower data rate. As soon as the car drives away, you've now got a very good signal, and then the device can be told to move to a much faster data rate, and more importantly, less time on air, again, which actually means that you can control and reduce the power that the device actually uses. So that key feature in itself is the thing that really makes the difference to how well LoRaWAN works. And all the time you're trying to get it to run to the fastest data rate and keep the energy that it uses down to the minimum. I won't go into too much detail on this, but we talked a little bit about the different classes of device. So I described in the original sequence, the class A device, where basically you have a packet, the end device sends a message, and then it shuts down, goes back to sleep. It knows roughly 1 second later when to open up its receive window. It listens to see if there's a preamble. If there is, and it's for him, it carries on listening. If not, it goes straight back to sleep. And if there was nothing received in this first window, it would do the same for the second. But basically, if nothing was being sent back down to it, at that point, the device would just go to sleep. So clearly for a class A device, it's the most efficient if you're just a battery powered device and you're a sensor. However, if you want to talk to it, you can't effectively talk to it unless the device is going to send you a message. So there's a couple of different classes defined to allow you to do that. If your device, and I'll jump straight to class C because that's the next simplest one. If your device is mains powered, then it's fine because you can afford to have it continuously listening. So what it actually does is it sends the packet it's going to send, and then it just basically opens up a window and listens continuously at the end of that. So if you want to control street lighting, for instance, this is a classic example where you can just talk to the device at any time. It's connected to the mains, it can continuously listen, and it doesn't actually have a problem. The one that's the interesting one is where you've got a battery powered device, but you still want to be able to talk to it. And we have what's called class B, which is where basically the network sends out a beacon every 128 seconds, and that device wakes up. And bearing in mind these devices, the idea is that they could have very low cost, so they're going to have a very low cost crystal or potentially no crystal at all. So we're effectively giving them a reminder every 128 seconds of what the time is. But when we set the beacon up, we also say, okay, we set up predetermined receive window slots for it. So within that 128 seconds for this device, we're telling it to wake up 8 times. And again, it'll do the same. If there's anything, it'll listen at that point. If there's anything for it, it will decode it. If not, as soon as it's received the preamble and said it's not for me, it'll go back to sleep again. So this now gives us the ability to talk to a battery powered device and actually give you some very quick information and a quick way of actually talking to it. So again, the different classes are used for different types of application. So just a little bit about the security side of it, and also the protocol stack. So within the LoRa itself on the device, you have the physical LoRa device, and then you have the LoRaWAN and the link layer adaptation, and then the application layer that sits on top of it. And you can see that the LoRa device is really only making the connection between the device and the gateway. And then when it goes across to the network server will decode and detect these bits, and then the application layer is basically sent on to the application side of it. So just a little bit about security and the different levels of security. So we've talked about the security itself. So it uses a mutual authentication and integrity protection and confidentiality system. And I'll describe a little bit in the detail of what it means to the frame, but effectively the end device talks to the network server through a mutually authenticated link and an end-to-end encryption on the application server. And we also have a join server. So when the device first starts up, we tell it which join server to go to. And that join server has what is called the root key for it itself, along with the end device. So that root key will allow it to enable it to decode and join and create the actual session keys that it's going to be using whilst it's actually doing the communication. So for each end device, it's effectively set up with a unique root key called the app key, and then it has 2 other unique identifiers with it. The first one is the dev EUI, and the second one is the join EUI. And in previous versions of LoRaWAN, this was sometimes called the application EUI. But these 2 ones are addresses that come from the IEEE organization, and they have to be supplied to the end device. So each device has a unique root key as well as these other identifiers. So the way it works from the frame side of it within the LoRaWAN protocol itself, I'll start really with the application side of it. So we have the clear application payload that we want to do, and effectively it takes the dev address, the frame counter, and bearing in mind this frame counter is unique for every device and counts both uplink and downlink frame counter. And then it has the app session key, and it's the app session key that it's created from the root keys as part of the derivation when it first joined the network. So it uses all of those to encrypt using AES 128 for the payload, and then effectively puts the encrypted payload into here. And then the network server has something very similar. It has the link control layer, has the dev address, and again, the uplink or downlink frame counter. And it takes all of that and creates effectively the MIC out of it. And that MIC is then transmitted so that when the end device receives it, it can decode that and check that that message integrity code lines up with what was sent across the actual network. So all of the LoRaWAN security is based on those two security methods. And again, I won't have time to go into a lot of detail here, but if you want more information, then look on the LoRa Alliance website. There's a whole set of security white papers and things on there to actually go through it. So one of the other things I talked about, and again, this is one of the things you almost get for free if you're using LoRaWAN, is there are really two methods that you can use for geolocation. As I've said, if you want to put and you want really accurate location, then obviously a GPS on the end device is the most reliable way of doing it. But that takes up a lot of power. Just to start and find and acquire the satellites and things is going to take you a lot of time and effort. And so it uses an awful lot of power for what is the majority of cases where you don't need to know quite accurately what you need. If the device you want is in the field and you want to know roughly where it is, this is good enough. And it can use two things. It can either use the received signal strength indication, which is received by these different gateways here, or it can use the differential time of arrival for finer accuracy. And the way that actually works is the end device will transmit. You know exactly the position and the time of each of these gateways. So these gateways, as well as reporting the normal application message back to the network server, they also send this fine timestamp information back to the network server as well. And that information then can be passed to a geolocation solver, and it can use the difference in time of arrival of these devices to more accurately position roughly where, or position down to sometimes up to 3 meters or better if you've got a clear line of sight where that device is. But again, it's usually close enough if you're somewhere where you want to make sure it's inside your factory or whatever, but you don't have to make sure that you have, first of all, a GPS signal to it, and you don't want the extra cost that you have by putting a GPS onto it. So really with those methods, it's a very simple way of doing it, and you effectively get something for free because the device is transmitting anyway and you can collect it. If you want a little bit more information, then you could get the device to possibly send a couple of messages at each location, and that again will help improve the accuracy of what you need. So I've talked a little bit before about the regional parameters and where we are with those. So one of the key things is the LoRaWAN works in the sub 1 gigahertz ISM band. And for those who know anything about it, there are different regulations across the world, depending on which country or region you're in, that determines how you actually want to use that ISM band. So really what the LoRaWAN has done is adopted and adapted the different regions to be able to say, and we create effectively a regional parameters document that says, if you want to use your device in Europe, well, these are the frequencies that you can use it on. And again, that's not set by us, that's part of the regulatory requirement. But then we actually say how to use LoRaWAN so that it can make the most of whatever channels it's got. So we define some join channels, and for Europe, there are 3 join channels. For Asia, there's 2 join channels, but we define what those channels are. And then once you've joined to the network, you can then be moved to anywhere within that time slot of frequency channels to avoid other traffic that may be on around it. So again, the parameters allow you to set the device up. For North America, they have to have frequency hopping, so they use 64 channel system. And again, we define how you would use LoRaWAN with that 64 channel. And effectively, we can see parts in Asia which use a combination of both. So some using more of the ETSI sort of style, and some are using the FCC channel hopping type ones. So we set all of those up based on how you need to operate within that particular environment. The other things that's controlled by it is whether there's duty cycle restrictions. So obviously in Europe, we have duty cycle restrictions. For North America and for others, they have dwell time, so they're not allowed to transmit for a certain amount. There's a limit to the amount of time that they can actually transmit for. And then whether or not they listen before talk. So all of those has an impact on the data rates that are allowed. Obviously, the maximum power is different and can be configured again for each of the different ones. And then the channel plans and the channel masks that are used. And really then the final one is this maximum payload versus the data rate. Because if you're trying to make sure you apply any dwell time restrictions and you cannot transmit for more than 2 seconds or whatever, then that will limit the amount of data that you can send in any one go. And you then have to send it as multiple messages. And it also allows us, I talked about receive window 1 and receive window 2. We do something that's slightly clever for receive window 2. Normally receive window 1 is just using the frequency, for Europe anyway, is using the frequency that it was transmitted on the uplink. For receive window 2, there are a few special channels you can use for Europe, which actually give you a much better or less restrictive duty cycle and slightly higher power, so you can use those. And for North America, you have higher bandwidth channels which you can use for downlink. So again, this is all defined as part of the LoRaWAN protocol. So finally, just as I'm the chair of the certification committee, I just wanted to do a quick section on the certification program. So we've had now, since I started, and for the last probably 4 years now, we've had devices being certified. We've recently just hit over the 400 successful certifications done. And what we're really seeing is this is making a huge difference to the quality of the devices that we actually get in our networks. And more importantly, we're getting the feedback now that not only does it improve your confidence and reliability, by actually doing this, it reduces the cost later. A lot of companies who are doing this are effectively startups, and they have a great idea, but they struggle a little bit with trying to get a reliable device for it. And this really is a way of them being able to prove that, yep, they have taken on board, they can do all of the things that are defined in the LoRaWAN protocol, and they can actually do that. And the other thing we do is offer an ability to be able to measure the RF performance of an end device. If you have a poor end device in terms of it doesn't give the maximum output power it can do, it means when it's being used, it's always going to run at the lower data rates, which means there's more pollution to devices, and also there's more issues in terms of the network that the operators are going to need in order to get that coverage. So I think that was pretty much the time that I've got allocated for this used up now. So at this point, I'll pause and really sort of step back to see questions and answers.
Hi, Derek, it's Peter. Thank you very much for the brilliant presentation. You've got many questions. I think some of them will have been answered as we go, but let's go through them for completeness just to make doubly sure. So the very first question that came in at the beginning was, is LoRa communication a reliable one for nano satellites?
So one of the areas that is being worked on and is in the latest regional parameters document, we've always had the ability to do satellite communication where you talk to a gateway that is got a backhaul through satellite. We have just introduced in that what we call long range FSH, where we have the ability now to actually communicate directly from an end device on the ground to an overhead satellite. And there are satellites now in orbit which actually can receive LoRaWAN messages directly from that. So it's just been introduced in the latest version of the LoRaWAN regional parameters as new data rates to effectively allow you to do that reliable communication.
Perfect, thank you. We'll stick with satellites because we've got a few more satellitey questions. So in the case of nanosatellites, how can we make LoRa communication better? How can we increase the range, strength, less noise? Can you provide some tips, please?
So obviously one of the key things is with all these satellites, it depends exactly where they are and when they come over to you. So one of the things you have to be able to do to get a reliable communication is know when the satellite is visible for it. So at that point, there's a lot of synchronization that would need to be done with the end device to know which satellites it's talking to and when they're actually going to be visible for it. But obviously, as time goes on and we get more and more satellites lifted up, then the chance of being able to communicate will increase considerably with it, and that again will significantly help the reliability side of it.
Thank you. Okay, the next one is to do with different frequency ranges. So why do LoRa networks have different frequency ranges in different countries?
So unfortunately, it's nothing to do with the LoRa and LoRaWAN. The ISM band, which is the industrial, scientific and medical band, has been defined by the radio authorities and the ITU across the world. And typically in the 2.4 gig range, that's pretty much standard across the world. However, in the sub 1 gigahertz, every entity effectively has its own use and its own set of requirements for it. So it's not something that the LoRaWAN wants to do. It basically has to do it to make sure that it is compliant in whichever country it wants to work at. And that's why even when we do certification, for instance, we certify a device against a particular region to make sure that it's actually compliant with the regulations. We're not actually doing the regulatory compliance of it, but it has to be used within that regulatory constraints. So it's not part of the LoRaWAN or the LoRa Alliance that set this, it's the regulatory bodies that determine it.
Okay, so I'm going to ask a personal question, which I think may be further down, but just in case it isn't. So in the case that you've got a device which could end up anywhere in the world, say a tracking device like this rather nice rack one, which you could put in a shipping container, which could rock up in any part of the world, does someone make a chip that supports multi-radio, multi-frequency?
So it's something that is being done now in terms of the multi-radio. One of the key things that actually you need to do is when the device first wakes up, the most important thing is it has to know where it is to know which frequency to first transmit on. So there's a few things that we've been doing from the Alliance, and one of them is I mentioned the beacons for Class B. Well, those beacons actually can also be used to determine where you are. So when you receive a beacon, you can actually determine if you're in the States or in Europe, because before you're even allowed to transmit at all, you have to know which region you're actually in to do that transmission. So you can either do it by listening to the beacon, or if you've got some sort of GPS on it, you can use the GPS to determine your location. So even though you have a multi-regional device, actually being able to make sure you still stay compliant is actually the harder part than the device itself.
Perfect, thank you. The next one is to do with, this is again a theme which has cropped up a little bit, it's about radio licenses. So what are the legal issues faced by a satellite carrying LoRa? And I think there's a separate part to the question, which is, should the user get a radio ham license for their application?
So currently, there is no need for it. Again, it's still using the ISM band from a frequency point of view. So even though it's communicating with a satellite, it's actually still doing it within the ISM band. So there is no need for a radio license or anything like that. And again, it's part of the unlicensed band, shall we say. So it doesn't mean that you need a license of any sort to do so.
And that's, I think, one of the beauties of LoRaWAN, which is probably why it's getting so much traction, which is you can just go and do it, basically.
Exactly, yeah. And we've seen so many people now who've just had, I've got a brilliant idea, I want to be able to control or run this, and literally they can go buy a gateway, they can set up the gateway. It's all part of the unlicensed band, so they don't even have to get a separate license to do it. They can actually just run the device as it stands, make the backhaul connection to a network server, and they're away. So it really is that low cost flexibility. And more importantly, it's not like if you've got a mobile 3G, 4G connection where you're having to pay thousands or hundreds of thousands or whatever and license fee for the license. The license is available for you to use.
Brilliant. So I'm going to ask, I'm going to again move the questions around a little bit. So someone's asked about what is the Things Network and what's its purpose?
So the Things Network and the Things Network are part of the LoRa Alliance. What they're offering is the ability to connect gateways to it. So they've gone what I would say is a slightly different way of setting up a network, but effectively allowing you to take a device, set up your own gateway and connect it back through the Things Network for effectively for free. And they offer two options really. They have the ability to just to have a connection, which is a sort of best effort type connection, and you can set it up using the Things Network. Or if you want a better quality service, you can move over to their industrial platform, which allows you to do that.
And I think speaking personally, I've used both, and they're both excellent. And are they the only supplier? I mean, if you want other companies that supply network servers and that sort of thing, what other companies would come to mind?
Yeah, so there are lots of other companies that come to mind, ranging through from. So I'm just trying to think of some off the top of my head. Actility, OrbiWise. I'm trying to think of some of the ones across in the States now. Senate, I know, run their own network servers. So there's a lot of, and part of the Alliance, again, if you want more, you can go in and look on the LoRa Alliance website and see all of the network server providers that are effectively offering that as well.
Brilliant, thanks very much. Okay, so let's have a look at some other questions here. So this is a good one. Are there any limits to the amount of devices on the network before stability of the network is compromised? So I guess realistically, in say a dense urban environment, how many sensors could you have chirping out their data?
So this is a really interesting one, and the reason why I talk so much about the adaptive data rate control is this is what really allows you to densify your network. So if you can imagine you have a single gateway in the middle of a city center, and you're getting to the point where it's getting congested, shall we say. And when I say congested, there's no real limit in terms of the number of devices that a gateway can handle, because it doesn't have to register them or track them. It can be an unlimited number of devices. What you actually get down to is what's the time on air that each of those devices is actually transmitting that will determine the maximum throughput you'll get at the gateway. So what you're able to do is, if you just have one gateway in the city centre, then clearly all the traffic is going to concentrate in that one gateway. And as soon as you see that, it's simple enough to just go and put another gateway, I don't know, a mile away, a kilometre away. And then through the adaptive data rate control, what it will do is the network will see that there's a new gateway. It will start receiving the messages that come from the different devices, and it will effectively switch over and say, well, instead of them talking at the slowest data rate to gateway number one, they're now very close to this new gateway I've just put in, so they can now actually talk to gateway number two. But because it can then send up the data rate that it's working on, remember the sensitivity is going down, so it actually means that it's now not causing so much pollution and so much interference for that first gateway. So every time you get to the point where you need more density in your network, the simple solution is you don't have to do any re-engineering as you would with other systems. You literally can just put a gateway in, and the network server will recognize that new gateway, sort out the appropriate data rate for the device, potentially using the new gateway, and then effectively tell it to reduce its data rate. And if necessary, if it's very close, it can also get it to reduce the power. And therefore, it's helping the device because it's not using so much power, it's transmitting at a very fast rate. But more importantly, it's not polluting the other gateways that might be a mile or 2 miles down the road from it.
Okay. Another question is, if you were a council or rail track or network rail or something that's wishing to put in your own LoRaWAN network, are these gateways tens of thousands of pounds each, or hundreds of thousands of pounds, or cheap things? Or
so they're a lot less than that. largely depends on what's the environment you want to put your gateway in. If you're looking at an inexpensive indoor gateway, they can start as low as, I don't know, $200 US, $300 US. If you're looking for something that you want to mount outside and it's got to be full IP66 or 67 or whatever rated, then they could go up to a couple of $1,000. But in comparison to a normal base station, they are trivial and very, very much lower. So it would mean that you could, for a few gateways and a couple of £1,000 or dollars, you could set up your own network.
So there's absolutely no reason why everyone on this call should nip out and start a network.
Exactly. Yeah.
Excellent.
And
That's what we like.
That's where we've seen a lot of the people that have actually been using it, and a lot of people starting up is, and that's why I mentioned that typical one is they have an idea, they want to monitor something, they do it locally, there is no corporate network, there is no sort of generic network available, so they set up their own, and then when a national network comes along, they might piggyback onto it and use it for other things, but then they revert back to their own network, and it's really that simple to do. And we've probably got, I don't know, probably over 50% of our devices are still on private networks.
Fantastic. Listen, questions keep coming on. We've got 30 questions still, so we'll answer as many as we can. So I'll move around a bit. So can LoRaWAN interfere with amateur radio frequencies?
No, it's very, very unlikely because we're effectively below the noise floor with that. It's very unlikely we would cause any interference with that, and it's very unlikely you'd even be able to detect that we're transmitting.
Okay, thank you. And without keep alive signals, I guess, between the network and the device, how do you know that end devices are still alive?
So this is really up to the application. How often do you want it to send you a message? And if you're talking of something that's a security or, as we mentioned before, the sort of smoke detector, you might want it to say, okay, once a week I'll send a message. But that's literally the only thing that you need to do. It's not really for the device's point of view. It's for your own peace of mind, shall we say, that it's there. Because there is no registration for the device, the device doesn't care whether it sends it once a day, once a month, once an hour.
And I suppose if you were building an application, it would be wise in any case to periodically say, you know, this is my battery life and I'm still here. So,
yeah, and part of what you get, part of the LoRaWAN protocol is every message you send as well actually gives you battery information with it as well. So yes, it would be worth, and we would advise that you do send, I don't know, weekly or monthly messages if you're not expecting very often communications with it.
Yep. Okay, thank you. So I think this one's partly been answered, but I'm going to ask just to be sure. Does the end device only transmit data back once the network requests? Actually, it's the way around, isn't it?
It's the other way around. So an end device in Class A will send an uplink. And obviously it's determined by the application when that is done, whether some sort of event has triggered it to happen. And then it opens its reception windows, as I said, either the 1 second or 2 seconds afterwards for when it can listen. If it's a Class A, if it's the Class C, then effectively you can send a message to it at any time because it's continuously listening. So depending on the application would be how you'd configure the end device, whether you want to be able to talk to it immediately, or if you just want to say every 20 seconds have the ability to talk to it and it's a battery powered device, then you'd use the Class B and set up those reception windows that every 20 seconds it would wake up waiting for a message if one was there for it.
Okay, and I suppose therefore when you're building an application, there's nothing to stop you sending parameters back to the device saying increase the uplink rate. So in other words, you know, if it's, suppose you're measuring, I don't know, temperature somewhere, if things start to get interesting and you want to know, have a higher frequency of measurement, you can always send a downlink message saying send me more stuff, right?
Yeah, and typically we also do that with some of the geofencing type devices as well. So the device sends its location and then it gets near the fence, and then you send an application message back to it that says, okay, instead of sending once every minute, start sending once every 10 seconds or whatever. And again, it's really up to the application as to how often and when it wants to transmit. And also you have the ability as well that if you send a message like the typical alarm one, and I didn't mention this earlier, if you want to guarantee the message is cut across, then you actually ask for an acknowledgement, so that they will definitely get a downlink message the next time that says, yep, I acknowledge that I have received your message and I'm now acting on it, or whatever. So with all of the LoRaWAN as well, you can send things as just an unresponsive, or you can get it to request a response, and that works in both uplink and downlink.
Okay. So here's a question, no doubt it's come from National Grid, perhaps. It says, how about cybersecurity issues with LoRaWAN? Can it be used within a substation environment?
So yes, we actually have had some, and I've been aware of some devices that are being used now in a nuclear type environment, where it's actually using it for the propagation side of it. So again, the security is there, it's built in. The fact that we have the frame counters is all part of that. There is no replay attacks you can do on this, because all of that is checked. So there is no reason from a security point of view why you can't use that.
Okay. Someone's asked about the slides, so we're going to aim to send them out after the within the next day or so after the event. So yes, the slides will be made available. So it's a highly popular. You've got more questions coming in all the time. Okay, here's this is a good and controversial one actually. How does LoRaWAN compare to Sigfox?
So really, they're different models.
Well, what is Sigfox first of all? I should ask.
Okay, so let me explain Sigfox. So Sigfox have a similar sort of LPWAN technology. The model that they actually use is slightly different. So they're not an open network like LoRaWAN is. Typically with Sigfox, and you don't quite get the same technical advantages as well. There's other limitations which I won't go into, but effectively the model for Sigfox is you effectively rent the equipment from them. They run and own the network, and you then pay as and when you want to use that network. So really it's a commercial model as much as anything, as well as the technology. They're not quite as advanced, I would say, as LoRaWAN is.
Brilliant. Someone said, brilliant speech. You really know the subject. Absolute pleasure listening to you. So that's good to know.
Thank you very much.
So that's answered live. Okay, this is a good one as well, very topical. So can these devices have a SIL rating? I believe the SIL rating's to be used in intrinsically safe areas. I think mines, for example, are a good example of that. So can they have a SIL rating?
So it's probably not a question I've asked. The reality is there is no reason why they shouldn't be. They're actually, when you look at the transmitting power of it, and for Europe, I mean, it's a 14 dBm or 16 dBi device. They transmit very, very low power in comparison to a normal mobile signal. So anywhere that you could use a mobile, there'd be no reason at all I could see why you couldn't use this, and certainly in places where you can't use mobile, as the power that's transmitted from these devices is significantly less. I can't see there being any issues from that.
Okay. Another good question on the topic of shipping containers. So if you were going to put, say, your little rack tracker on a shipping container,
yep.
Whose gateways would they use? And I guess that leads nicely into the sort of roaming side of
So yeah, it's been an interesting one, and again, this is one of the things that we've actually been looking at. Is one of the things we've looked at doing is actually putting gateways onto the ships themselves. So you could actually have a shipping container that sits onto, gets shipped onto the device. It then picks up a gateway with that. That gateway could then be backhauled if you want to keep track of it while it's actually in sail. It backhauls it through a satellite link. And there's a lot of work being done to reduce the backhauls, because obviously one of the key things for a satellite link from a gateway is you reduce the communication down as much as possible, because it's an expensive media to go by. And then as the device gets further into port, at that point, it could either then pick up a traditional mobile connection and actually get backhauled once it actually gets into the port. But this is then also where you need, as the gateway can go across the world, the gateway itself also then has to be able to transmit differently and switch to whatever frequency is appropriate for the region that it's actually being into. So now you're not just talking about the device, you have to have the gateway that's capable of doing the same.
Okay, thank you. Here's a really great question. Actually, it's one that it's close to my heart because I like building stuff too. So it says, does a cheap hobby kit or development kit exist for the home student user to learn more? And I was going to recommend one of those if you know what that is. But do you want to recommend one first, and then I'll suggest this one?
That looks like the rack one again.
No, this was this is the Sodak Explorer one. But what would
Okay.
you go first? What if someone wanted to start out and start building stuff? What should they do?
Yeah, so it's interesting. There's a lot of different devices around. It depends whether you actually want to create your own software for the device or you want to pick something off the shelf. What I'd look for is, personally, from my point of view, I'd be looking at some of the nuclear boards and things like that, mainly because Semtech offer a reference code for those devices. So you can effectively take the reference code straight from GitHub and put it onto one of those boards, and then you've got all of the LoRaWAN protocol built into it, and also they offer all of the multi-regional support. So again, depending on which country in the world you want to do it, I would suggest that's a good starting point.
Okay, and what should this chap, if he wants to Google search for something, what would they search for? Sort of LoRaWAN dev kit or
Yeah, LoRaWAN dev kits, and there are various, even on the LoRa Alliance website. If you look on the web page, if you go onto that, there's a showcase of devices. So we have certified quite a few different development kits as well. So on the LoRaWAN showcase, there are numerous dev kits and devices on there as well.
Okay. Now here's a question I think I can answer because I've done the LoRaWAN certification test. But it says, can the range be increased from 10 miles? Sorry, can the 10 mile range be increased by a repeater? Or I guess the other question is, can you get more than 10 miles out of it?
So it really depends on the line of sight. We've had people who have taken an end device and put it up into a weather balloon and then actually tracked it from somewhere near Bristol, I think, right the way across to the Alps. So then you're talking hundreds of miles. And so the range or the line of sight is what really determines. What you are limited to is, obviously, in terms of using it in the ISM band, that regulates the amount of power that you can transmit for. So the other way, obviously, to get more range would be able to transmit at a higher power, but in order to use the ISM band, you can't. So again, this is why actually just putting more gateways in is normally the simple solution. If you have something that's working on the end of its range, put another gateway nearer, it'll automatically switch over and you'll get the savings from the battery power as well. But if you've got line of sight, there's no reason why you can't get a couple of 100 miles out of it.
Got it. So you don't so much put repeaters in, but you just put in more. You have more of a star topography with just more gateways connected.
Yeah, we are looking, and one of the things that's being looked at the moment is a repeater type scenario where you don't actually have a physical internet connection to it. So, but that's something that the LoRa Alliance is working on at the moment, where you would literally just extend a LoRaWAN signal, but you don't have an internet connection, so you can't put a gateway in directly.
Okay. There's a question about cost. So I mean, I guess ideally your LoRaWAN gateways will be connected over kind of Ethernet backhaul or some sense. But the person's asking, is there not a risk of cost multiplication with multiple gateways reporting back over 4 or 5G? So there's the option to go over 4 or 5G, isn't there? Of course.
There is, yeah, and I mean, you could, if you wanted to, start sort of whitelisting or blacklisting in the gateway side of it, but effectively you don't necessarily want to restrict that. So the best solution is to try and get an internet connection. What you do see though is actually these are fairly small data packets that are coming in anyway. And okay, you've added a little bit of RSSI and signal strength and the time of arrival to it. But even then, when you backhaul it, whether it be over a 4G or a 5G, it's actually very little data that you're sending. So in reality, the cost of sending multiple messages isn't actually that much because it's very small packets of data you're sending anyway.
Yeah. Okay. I should ask, are you okay to continue?
Yeah.
How and Rick, are we okay to continue a little bit longer? I can see that 98% of the people are still on the
Yeah, go ahead.
Okay, we'll
Keep
just
going,
do a
Peter.
few more then. Okay, let's see. So we've covered the one about interference. A little bit about the encryption. So there's three questions that are similar. So one question is can it support AES-256 encryption? And someone else was saying the 128-bit is a bit old. So yeah.
Yeah, so obviously 128 is what the system is designed for. There are looking at other ways of trying to do it. We've certainly seen at the moment for all of the people who've actually tried to do this and anyone who's tried to break it, most of the issues actually come back to how the device is configured in the first place. So out of all the various reports that we've had on security and some of the issues that have been seen, I would say the majority, if not all of them, have actually been because people haven't configured the device properly in the first place. It's a bit like setting your own home router up and leaving the password as 123 or admin or something. So yes, we are potentially looking at future enhancements of it, but certainly everything we've seen at the moment, 128 has been good enough.
Perfect. Okay, this is a good question. It's looking at the sort of roadmap, if you like. So how long do you see LoRaWAN existing in its current form before the next evolution or revolution?
I think there's a long way to go yet. When you actually look at where the alliance has come from, literally in 5-6 years, and when you look at it compared to other alliances and what's been achieved in that time, we've made significant strides in that time. The technology itself and the way it uses is so simple and straightforward that actually I think this has got a long life ahead. And once you start getting into the billions of devices, it means the technology is going to be around for a long time to come yet. Yes, we can always look at different things, which is why we've looked at adding the satellite backhaul into the networks and things like that. So there could be other future adoptions going on and potentially looking at other scenarios in terms of one of the things that's being looked at is active roaming, where you roam not just passively from one network to another, but actively. So there are sort of few small tweaks, shall we say, in LoRaWAN going forward. But I think the technology itself will exist for a lot of years yet to come. And as more and more devices use it, that will ensure that it stays there for many years to come.
Great stuff. Okay, and this is a question, I guess, also sort of relating, if you like, to the community aspect of LoRaWAN. So, and also, I guess, the TTN in a way. So, is there any scope for the public to put LoRaWAN gateways on air in the area to provide data coverage for other users? Would you say a Raspberry Pi or a suitable hat would work?
Yes, and people do, and that's one of the things that you actually get from if you connect to the TTN network, for instance. The TTN model is actually you can set up your own gateway locally, and then your gateway will become part of the network so that others can use it as well as yourself.
And I would add to that also, as someone who's done this quite a bit. So I would say go and buy a cheap, proper outdoor gateway because they're not that expensive. You can get them for sort of £200 and by the time you've messed around with the Raspberry Pi hat, power supply, plastic box for it, you've almost got to that price point anyway. So do the right thing for the community and put a decent gateway on top of your roof with a big antenna, and that will be fantastic.
Yeah, and then you'll be helping all the networks.
You'll be helping, yes. You'll and of course there's I think the TTN have all these sort of various community groups, don't they, who get together quite a lot online. So there's quite an opportunity to to find other folks in the area who would want to get involved with this too, I think.
Yeah, and there's a lot of other companies as well that are offering similar sort of functionality and similar sort of advice as well as Semtech themselves offer a lot of support for the community.
Right. Okay. So we're left with some of the more complicated, very hard, long to read questions. Okay. So this is this is a nice simple one still. What is the time when you would consider LoRaWAN? Is it just for external networks mainly, or can you use it indoors too?
So I would say the majority of private networks, certainly the first ones, were set up as indoor, and they were typically used for warehouses, for tracking things in there or monitoring it. So it will work extremely well indoors. Again, you've got that sensitivity, and with that sensitivity, it allows you to actually get through walls and down into basements and things like that. So one of the areas it's actually very well suited for is indoor. So there is just as many indoor uses for it as there is outdoor, and there is no real limitation for using it indoors. Probably the only thing that's slightly harder if you want something indoors, and especially if you're going to put your gateway indoor, is if you want to do the sort of TDA, time on arrival type geolocation, then the gateway will need some sort of GPS time reference to it. And that's the only issue if you take it indoors. But for just the straightforward monitoring and controlling of a device, an indoor gateway will work perfectly.
All right, thank you very much indeed. The next one is around what have you heard of something called the helium network, and how's that different from LoRaWAN? What's helium?
I haven't heard of that one, so
I think I can answer that. I think helium, I think, is an American outfit that have linked up. It's LoRaWAN based stuff, but you collect sort of Bitcoin credits or some sort of cryptocurrency in exchange for hosting a network. So I think it is a LoRaWAN network, but uses a different charging model to try and increase the rollout and
okay. I mean, the one thing I would say from that is, I mean, we have seen a few other places where they're using just the straightforward LoRa rather than LoRaWAN. And what I would always recommend is, as long as it's following the LoRaWAN protocol, then you get all of the added advantages of using LoRaWAN, which is hundreds and thousands of devices available for doing that, as well as all of the built-in security and stuff like that. So as long as it's using a LoRaWAN network, then it sounds great.
Okay. Another satellite question. This is an interesting one. I think the answer to this is no, but I'm not sure, so I'm going to ask you to be sure. Is intra-satellite network possible with LoRa?
I wouldn't like to say.
I thought that the ISM band doesn't allow you to transmit down from the satellite.
You can transmit. I'm not sure is the answer to that question. Rather than say the wrong thing, I don't know.
So the person who asked that, there's some research to be done, because if Derek doesn't know, no one does. So therefore, something to do some research afterwards. Okay.
I guess the question would be is whether it's, I mean, for intersatellite, whether it's actually the efficient way of doing it, because you don't have the constraints. So I think that's partly why it's probably not been investigated too much at the moment.
Yes, indeed. Okay, it's an encryption question. Is it possible to enable encryption only for the end device to the gateway? So they want to encrypt in the uplink, but not encrypt on the downlink.
Not easily is the question, and I'd probably like to understand why they were looking at doing that, because what you can do is, if you really don't want to do that, there are gateways that you can run effectively mini network servers on. So what I would suggest in that case is you actually run a network server on the gateway, and then that will give you the gateway to end device network security as well. And I would suggest that's probably the better way of doing it.
Makes sense. Okay. Okay, so this is another question about sort of who pays for what. So who pays for the network, gateways, etc.? Are these free for users to use? And is there a distribution of these across a wide geographical area? Or does the network need to be set up by users? There's many questions there.
Okay,
so who pays for the network?
So really this boils down into the two models. We've talked a little bit about public networks and we've talked about private networks. And when I showed the graph of the 160 odd countries, that's a combination of public networks where the operator will effectively put a gateway, and quite often they'll put it out onto the same tower as they've got their 3G, 4G masks, etc. And then in which case it's actually the public network and you're paying the operator for the use of that service. And then you've got the other one where you've set it up yourself as a private network, and that could be you personally, or you've clubbed together with someone else and set it up as a private network. And in which case there are no separate costs for you, obviously, except for whatever you'll pay for your network server, whether it be from TTN or from one of the other network server providers.
Okay. There's a few questions about learning more stuff about the tech. I'm going to group these together. But if someone wanted to study this, at a sort of fairly academic level, where would they go to find good resources about modulation schemes and the standards and the specs?
So I think there's a few places. I know Semtech offer quite a lot of educational type information. What we also have within the Alliance is an institutional membership of the Alliance as well, and we have various work groups with them. So if your academia is interested, then You can also join the Alliance and get all the visibility of the specs and everything else that goes with it.
Okay, let's have a look. Oh, this is an interesting one. It's about firmware upgrades. So can you specify firmware updates over the air in a bit more detail? Can this be done, really?
Yeah, so what's actually been done, and we've proven to show it's worked, is I talked about the normal operation of it, and that's as a unicast, and the security keys are basically unicast security keys. What you also get the chance to do, and this particularly works for Class C and potentially for Class B, is you can do a multicast. So the firmware over the air, basically, you set your device to receive, and that's typically as a Class B, or if it's a mains powered one, as a Class C, and then you transmit as a multicast using the multicast session key. Then every device that's within range of it can actually receive it and pick it up. And we've done lots of work with different algorithms that say, actually, you can transmit this, and with a LoRaWAN network, because it's in the ISM band, you'll expect to see some packet loss. But the algorithms they actually use is, I think we're down to the point where out of 110 packets, as long as you receive 100 of them, then you can decrypt it. So it's done by using a multicast arrangement where a gateway will multicast to a whole group and will effectively download the firmware build. But again, you want to keep that firmware build down to the minimum, because you are multicasting, so you're using up a lot of the allowed bandwidth, especially if you're a gateway. So there's time on air restrictions, obviously, or dwell time and duty cycle restrictions. So the multicast is a good way of doing it because you only transmit it once. But again, you need to be aware that actually it's quite an expensive resource because you are using the gateway's transmission capability.
Okay, I think I'll do one last question. Actually, well, depending on what the answer is to this, I'll maybe one more after this. But I'm quite looking forward to it because I don't know this acronym. It says how to use tiny GS stations with LoRa. There's quite a lot of questions relating to something called tiny GS. Do you know what that is? No, because the other one is can you please brief SAT NOGs and tiny GS network in a LoRa perspective? And then there was another one about tiny GS, but I don't know what that is. Okay, so we don't know.
I'm not aware of that, no.
Okay, no problem. Okay, in that case, let's get rid of those, and we'll do one last question. Let's have a look. Is the minus 148 dBm sensitivity post Viterbi? Otherwise, the channel would be very narrow. What's the range of chirp rates, etc.?
So it is configured as part of the chirp rate. So the LoRaWAN uses a standard chirp rate to actually do this. I'm not sure what the actual figure is off the top of my head, but you're always chasing the theoretical limit when you start looking at those spreading factors and the different ways of actually using it.
Okay, well, perfect. Thank you. Listen, so I think we've worked extremely hard, and this has been an absolutely amazing, fantastic presentation. I've enjoyed every minute, but clearly the audience have too, because I would say of the 160 odd people who dialed in at the beginning, the vast majority is still here, and there's been some really fantastic questions. So thank you so much on behalf of the IoT Hereford and Worcester local network. Well, is there any closing words that you'd like to say?
So no, just thank you very much for the time to do this. I've certainly been very enthusiastic in all the time that I've been working on it. I've been working on it since 2014, and I can see in terms of all of the work that I've done from a technical point of view, this has the most ability and the most ones. And even when I was in the role as sort of like trying to promote it and sell it, is normally you go to places and you have to do a sell. This was always the other way, that I've thoroughly enjoyed working with it because people really want to know and understand it. And so from my point of view, it's been great, and it's been fantastic to have the opportunity to talk about it. So thank you very much.
Well, thanks again. And on behalf of Laura Alliance and Derek and Rick and myself, I'd like to thank all of those that have dialed in today, giving up part of the evening to listen to this. So thank you to the IET members and those from the other organisations who have joined, because of course your participation in this makes these things possible and makes them worthwhile. So we've been delighted to deliver it to you, and thank you so much.
Excellent presentation, yes, and some fantastic questions. So we'll see you again next month, guys.
Yep, and the presentation will be sent out, right? And we are going. This has been recorded and will appear on the IET channel in due course. Perfect.
Okay.
Great. With that in mind, have a lovely evening and see you again soon.
Thank you
Bye
very
for now.
much. Bye-bye.